Um, yeah, hello everyone. Welcome to the Crunch seminar this week. So this week we have two speakers from our group, and they will each give a paper review and on our latest paper. So our first speaker is Somdatta, and Somdatta, I think you can share the screen now. So
I'll share it.
yeah, Somdatta will present a paper review with the title Parametric Deep Learning Approach for Elasticity Accounting Strain Gradient Effects. And yeah, so okay, we can see your screen right now, and Somdatta, you can start.
So good afternoon, everyone. Today I would review this paper titled Parametric Deep Energy Approach for Elasticity, Accounting for Strain Gradient Effects. This paper was authored by Min Yuan, Cosmin Anitescu, Nef Alajlan, Timon Rabchuk, and Shawin Zhuang. To introduce this article, they start with saying that they have proposed a new parametric deep energy method, which is an improvement over the existing or the conventional deep energy method. Now, as they go, they say that in 1998, Lagares et al. Proposed this idea of solving PDEs using machine learning approach. However, due to the lack of computational tools then, the concept did not gain much popularity. And this key idea which comes from there is to minimize a loss function, which is the residual of the domain, residual in the domain and on the boundaries of the underlying PDEs at specific collocation points with respect to the weights and biases. This was based on solving the problem using the strong form of the equation of the problem. Now, in 2020, Samanigo et al. Proposed the idea of deep energy method, and that was for solving the problem using the weak form of the governing PD, which has shown applications in elasticity, plates, phase field models for fracture, and piezoelectricity. Now, instead of relating the cost function to the underlying boundary value problem, it is expressed in terms of the potential energy of the engineering mechanics problem, which reduces the requirements of differentiability of the basis functions. This is because we require lower order of differentiation in a weak form of the equation, and also it automatically fulfills the homogeneous Neumann boundary condition. This approach is relevant to engineering problems which are directly based on energy formulation, like the phase field modeling of fracture, and has an advantage that it automatically fulfills the underlying physical laws. However, this approach has an associated issue. The downside of this approach is that it introduces integration errors, and not all governing equations can be cast in the form of an energy minimization framework. To alleviate that, the authors have proposed a parametric deep energy method approach, where the proposed approach is capable of solving problems in elasticity and strain gradient elasticity. Now, why strain gradient elasticity is so much focused here is because strain gradient problems are difficult to solve using finite element method due to the stringent requirement of C1 continuous basis functions. In this approach, instead of training the network in the physical domain, it is trained on a parametric domain, which is also referred to as the reference domain. Therefore, the inputs are naturally normalized, preventing the vanishing gradient problem. The mapping from the physical domain to the reference domain is accomplished using the NURBS basis function, which is commonly used in isogeometric analysis. This provides simultaneously the quadrature points to approximate the total energy. Like we have quadrature points, we normally use quadrature points when we are solving the variational energy formulation, and that is also used in the NURBS basis function. So we have two, we can serve two purposes.
Also, I have a question.
Yeah.
So you apply the differentiation on this problem, the PDEs, because when you do a deep neural network, you have to do backpropagation, and backpropagation requires you to do a chain rule or a differentiative derivative. Oh, that's correct or no?
Yeah.
Yeah. Okay. Thank you.
Since the loss function contains functional, the accuracy of the problem relies on methods which can numerically evaluate the integrals. Now, let's get a basic idea of the mathematical formulation of the physical system. So the parameterized PDE is expressed as shown here, where Lx defines the differential operator and is defined using the primary variable u, and the model parameters lambda, and it is equated to the load term or the source term, and the boundary values at the kth boundary is defined using b of k, and it is defined over the primary variable u. Now, um, since the solution of the system of the equation is specified at the boundary, so this can also be called as the boundary value problem or the strong form of the system. Now, instead of solving the strong form, the solution of the system can be obtained by finding the stationary point if one can reformulate the system in the form of a total potential energy, taking the advantage of the variational method. So that is the weak form, where we define this in the strong form in the strong form as the total energy of the system is defined as the difference between the internal energy and the external work done. And the external work done comes from the applied load or the applied load. And the optimization problem is recast as minimize the total potential energy, given that the primary variable lies in the in the space of admissible trial functions, and the primary variable u is constrained by the boundary conditions. Now, to find out the stationary value, we define the variation of the equations yielding del of the total energy, the total potential energy, using we reformulated using the test function, where eta is the test function, and this holds true for any delta u satisfying the boundary condition. Now, the variational formulation can be rewritten as del of pi equal to del of u minus del of w. This is one way of getting the variational energy. There's one more way in which we can do it, that is by using the principle of virtual work. That has not been specified in the paper. Now, this is the approach, the parametric deep energy method, in which the underlying problem and the related integrals are solved in the physical domain. And the authors have adopted the concept of isoparametric elements, which is common in isogeometric analysis, and have converted the formulation from physical domain to the parametric domain. So each of the edge of the physical domain has been mapped to one of the edges of the parametric domain. This parametric domain lies in the interval of 0 and 1, and a square domain is assumed. Now, the physical domain is, which is this letter H, is mapped to the parametric domain. The formulation of the total potential energy is minimized in the parametric domain. And the potential energy of the system can be rewritten as, if written in the physical domain, it would be over omega x. And when we write it over the parametric domain, instead of just having the energy term, we'll have the determinant of the Jacobian matrix, which contains the coordinate transformation from the physical domain to the parametric domain, and it is integrated over the volume del V in the parametric domain. The components of the Jacobian matrix can be calculated by finite difference approach or any numerical procedure. Now, in this proposed approach, the concept of isogeometric analysis is employed with the help of non-uniform rational B-splines as the basis functions to perform the interpolation so that the Jacobian can be computed easily. A brief introduction towards what NURBS basis functions and B-splines have been provided, how they have computed the basis functions, and how they are used. Now here, they have used the Gauss quadrature formulation to approximate the integral of the total potential.
From that, I go back. There are lots of people who don't know IGA, so we spend a little time to what is this here?
Okay, so when we construct a univariate B-spline, we define the basis function using this recursive formulation, where P is basically the degree of the polynomial. And since this is obtained recursively, at one point when my P is 0, the basis function would be defined using 1 and 0, where xi I is the natural coordinates of the system in the parametric domain. And we find out once the basis functions are obtained, the next step would be to obtain the 1D B-spline functions, which is defined using this formulation. This formula, the NURBS basis function in the 2D parametric domain is associated with the polynomial degrees P and Q, is defined using the R that we get over here. This is multiplied for the x and y direction, and once we multiply them, we have this formula. Now, finally, when we backpropagate it, we obtain, okay, so on the parametric domain, these are the points that are defined, these are the natural coordinates. On the physical domain, these are the blue points that we see, they are basically the control points. So here we use the control points to find out the find out the coordinates of the on the natural coordinate system, using the natural coordinate system. Now, the reference domain is
and from data, this you can do also if you have holes, right? If you have multiply connected domains, you can still do the same thing, right?
yes.
Okay.
Yes. And here they have used the Gauss quadrature formulation to approximate the internal potential energy of the system. The reference domain is discretized into smaller elements, and the integral of the strain energy is calculated by the summation of the smaller integrals in each integral, and is which is approximated as by the strain energy evaluated at each quadrature point. So the total potential energy is approximated as the summation of E is equal to 1 to n, where E stands for each of the elements, and this UE is the energy of each of the element. Now they have converted that into the natural coordinate system, and they have used the Gauss quadrature points, which is nx of p. Nx is the number of Gauss quadrature along the x direction, and ny is the number of Gauss quadrature along the y direction, and they have summed up the energy. The transformation from the physical domain to the parametric domain is performed by the change of coordinates from the physical coordinate x to the natural coordinates xi. This is done by using the Jacobian matrix and the inverse of it. Now, the necessary derivations with respect to the physical coordinates. So here my physical coordinates are x1 and x2, and they are converted to my to the natural coordinate system using the Jacobian transverse. And this Jacobian transverse has been used in numerous instances to convert the strain, convert stresses, and so on and so forth in the paper. Now, advantage of this approach. First, the input values are naturally normalized due to the coordinates of the training point being only restricted to 0 and 1, since the integral is performed between 0 and 1. Therefore, the convergence of the loss functions tends to approach the optimal value faster than the conventional training on the physical domain. And secondly, the training on the reference domain can be exploited for further training different problems due to the same geometry on the parametric domain. Now, in my opinion, I think transfer learning can be used to train different, can be used in this kind of method, where they could obtain the solution for other physical domain, since the parametric domain is the same. Now, they have shown applications on elasticity, and elasticity first. So here they have mentioned the elasticity in E1, epsilon 1, epsilon 2, and epsilon 2, This is the basic plane strain problem, where since that is why epsilon 3 is 0. Now, first problem that they have shown how they have converted the formulation from the physical domain to the parametric domain, the epsilon 1, epsilon 2, and epsilon 2. Now, first they have solved the Timoshenko beam problem, where a beam of length 8 meters and height 2 meters is subjected to a parabolic loading on the right edge. The Dirichlet boundary conditions are specified on the left edge, and plane strain condition is considered here. So this problem has the U and V, the displacements U and V, they have the analytical solution. So they have used this problem to check the accuracy of their method. Now, solving this, they have used three kind of data sets. The first one is a 10 cross 10 data set. The second one is a 30 cross 30, and the third one is a 50 cross 50. They have used three kinds of activation functions, and they have made a comparative study which shows that and they have shown the results for all three of them. The displacement error in X and Y direction using the tan H activation function is the one they move ahead with. And the results of continuously differentiable exponential linear units, they don't find it stable, because according to them, it's like since the range is between 0 and 1, the convergence is not guaranteed for continuously for CELU. And tanh or sigmoid activation function is more efficient for the input within the range 0 and 1.
The way it's been optimized.
Okay, I didn't check how it looks actually.
Okay.
So yeah, and the neural network, the boundary conditions, they have been constrained using the lift solution, and they have shown the energy norm and the L2 norm. They have used only one optimizer, that is the LBFGS optimizer, and the network architecture is three hidden hidden layers with 30 neurons each. The second is the annulus problem, which also has an analytical solution. So they have used this to check the accuracy, in which a thin disk has been subjected to an internal and external pressure. Plane stress conditions are assumed, and here, due to problem symmetry, they have worked with only 1/4 of the problem, a quarter of the problem, and it has been mapped to the reference domain, where each edge has been mapped to one of the edges in the reference domain. Here also they have used two data sets of 50 cross 50 and 80 cross 80, and the learning rate, they have used a higher learning rate for 80 cross 80 data set, saying that they have chosen this larger learning rate because of the explosion of the solution. When they have smaller data set, the solution explodes. So that is why they have used a larger learning rate. Also, they have made a comparison with the conventional DEM, and it shows that using the parametric DEM, the L2 error norm and the energy error norm are lesser than using the conventional DEM.
Hi, Somdatta.
Hi, Andre.
I have a question. So do you know whether they use the conventional like normalization techniques for their DEM method, like scale the 5 to 1 divided by 5? So
I don't think they use it because, I mean, since I know all the authors, so they don't use the normalization. And
okay.
I think since they are saying that the work is carried on using in the parametric domain, so since it's already constrained in 0 and 1, I don't think the input is required to be scaled. What do you think?
Sir, could you repeat that again? Sorry, I didn't quite.
So it's like the input is already scaled in the domain 0 and 1.
Oh, input. No, I just now I was asking, like, so if you look at the coordinates, it's from 0 to 5. So you mean they already scale that to 0 to 1 or not? So that
This
is
is
my question.
physical coordinate in the but the integrals are being done on the parametric coordinates. So first they're converting into parametric coordinates, and then they're doing the then they are training the network.
I think he's asking for the standard DM,
Yeah,
not,
yeah, it's
not the
standard
parametric.
DEM.
Oh, in standard DEM, I think I'm not sure if they have done this using if they have normalized it in the standard DEM and have given the results. I'm not sure on that.
Okay, thank you.
So in the parametric DEM, it converges faster than the DEM in all cases. Moreover, the loss value with more training points in both the parametric DEM and DEM is much smaller as the number of training cases increase. The L2 norm and the energy norm of both the parametric DEM and DEM converge during the training progress. The more important is that the parametric DEM always gives more accurate predictions. In all cases, during using more data, higher precise solutions would be obtained. In general, the parametric DEM is clearly more efficient than DEM at least for for this specific application, because the data is automatically scaled within the unit domain, and it prevents the gradient vanishing problem, which causes slow convergence in the original DEM as long as tanh and sigmoid are used as the activation functions. The third problem is the problem with a plate with circular hole, where an infinite plate is considered which has a circular hole and is subjected to uniform traction. Now, this problem is assumed for a plane stress plate. Traction boundary conditions are applied on the boundary. Here they have used the optimizer as the LBFGS, and the network architecture also remains the same. They have applied lift solution to exactly match the boundary conditions as specified in the physical domain. And there are also the analytical solutions available for UV and the stresses, the radial stresses. Here they have made a comparison with as they increase the number of hidden layers, they have shown that with a larger network, they get a lower L2 norm and an energy norm, which is obvious. Now, the final application is the application on strain gradient elasticity. Now here, higher order strain gradient theory is commonly used to account for the size effects. The strain gradient theory proposed by Atlan and Afantis is used by the authors in this work. Only three material parameters they describe the non-local effect in elasticity: the two Lame's constant and the strain gradient coefficient, which is defined using C. Now, in an isotopic gradient dependent linear elastic material is considered. As the strain energy density can be expressed as half of lambda epsilon II epsilon jj mu ij mu ji. This is what we normally use in the elasticity. The additional strain gradient term is this part, where it is multiplied with the strain gradient coefficient. Now, the strain energy of the body, apart from the Cauchy stress tensor that we normally use in elastic material, they have an additional third order tensor of mu and kappa, where there's the double stress term and the strain gradient. They are defined using the derivative of psi with respect to epsilon ij, and this is the Cauchy stress tensor. And mu and kappa are also defined using the derivative of psi with respect to kappa and with respect to kappa. The work done by the external load is given as this, where Fi and Ti are the components of the body force and the tractions respectively. The new term Qi is due to the double stress that I showed in the previous slide, and Dui is the normal, the directional derivative of the displacement, and is defined as NLUIL, where Ni is the components of the outward unit normal on the boundary. On the boundary, the total potential energy is obtained as this, where everything remains same except for this, the second term and the last term. The above equation yields the strong form from the weak form based on the equality as we apply the principle of minimum total potential energy, and it leads to the governing equations as this, where sigma is the tensor product of EI, EJ times sigma IJ, and the components of the total stress is defined using this. These are the boundary conditions, and the same annulus problem that was solved using elasticity has been solved here, where the analytical solution for this problem is expressed as this, where A, B, C, D, the constants, the four constants, they are determined by using a system of algebraic equations. I1 and K1, they are the modified Bessel functions of first and second order, and R defines the radial displacement, and C is the gradient strain gradient coefficient. Now, with a combination, so the strain field is evaluated as this. Now here, when they are solving the annulus problem, they have used two networks. So for the hyperparameter setting, two feed-forward neural networks have been used, which are connected to the same input as shown schematically. The first neural network has 4 hidden layers, whereas where the output is the displacement, and the second neural network has 4 hidden layers, where the output is the 3 strain components. The reason for such structure is because the displacement and the strain have 2 different length scale ratios. So epsilon basically has no unit, whereas the other whereas the other one has unit. So which can be considered as the activation functions and might lead to suboptimal approximation. The loss function in this case can be fully expressed as this, where U and W are the internal energy loss and the external energy loss. BC1 and BC2 are the boundary conditions, which are written as the mean square error loss of the left and the bottom edge. And E1, E2, E3 are basically the mean square error constraints from which is obtained by the difference of the strain components obtained from the neural network, from the second neural network, where the strain are the outputs, minus the strain gradients obtained from the first neural network, where displacement is the output. And gamma 1 and gamma 2 are penalty factors, which are chosen as 12,000 and 25,000. The displacement boundary conditions are pre-constrained, as in the elasticity example. The displacement gradient conditions are provided. Now, these are the E1, E2, E3, which I just described. Now, the total weights of the neural network are first initialized with values sampled from a normal distribution, and the biases are all set to 0. A grid of 2,500 collocation points in the domain and 100 points on each boundary are generated as the feeding data is used for the domain. Tanish activation function is used in the neural network, and the LBFGS optimizer is used for 120 epochs and a learning rate of 0.05. 100 random points in the domain. This is basically the output that they have obtained. So 100 random points in the domain on the boundaries are generated to compare the displacement of the radial and the circumferential strains, and and between the PDM and exact solutions. Apparently, the significant difference of the solution when we set up the problem with different strain gradient coefficients can be recognized. The magnitude of both displacement and strain of the solutions with high strain gradients are always smaller than the ones with small strain gradients. Furthermore, the differences between the solution with small strain gradient coefficient of C 0.01 and 0.05 are relatively small, but are significant when the coefficient is larger. This indicates that classical solution in elasticity is considered in a fine scale and may not be accurate due to the microstructure effects appearing at significantly smaller length scale. To conclude it, the parametric DEM is an extension of the original deep energy method and is applied to problems in elasticity and strain gradient elasticity. Here, instead of training the deep neural network in the physical domain, they have trained it in the parametric domain. The correspondence between the two domains is associated with a forward and a backward mapping through Nernst's basis function, which is commonly used in isogeometric analysis. In this context, Gauss quadrature is exploited. Now, this is what was written, but throughout the article, they have mentioned that they have used uniformly spaced collocation points. It can be that since they have discretized the domain into elements and could have used one Gauss quadrature per element, but that is also equivalent to a uniformly spaced point, but that was not mentioned. One advantage of the presented parametric DEM over the original DEM is that the inputs are automatically normalized within the natural domain, and therefore it prevents the vanishing gradient problem, which can appear when hyperbolic tangent is used as an activation function. In all cases, it yields better results in a shorter CPU time as compared to the original DEM.
Okay, thank you, Somdatta, for your presentation. So is there any question for Somdatta?
And Rui, I have a question for you. What is different? Of course, it's the IGA, but that's nothing really. But what is different from what you were trying to do? Basically, transforming this into some other more friendly.
So I think the starting point is what I'm doing is that due to something like the stress concentration near the hole, and if we do a transform, then we can put much less residual points in the regions that are far from the whole. And another thing is that by transforming, we can deal with some sort of discontinuity. So I think the starting point is kind of different. So for their work, the only thing I find that may be called an advantage is that the accuracy is slightly better. And maybe as they have said, the training time is slightly less. So in addition to those, I think, yeah.
There are two things going on here. One is the integral form of the equations, and the other one is the parametrization of the geometry and the transform domain. Which one contributes to what? Some data, do you know?
I think like the transformation domain that is helping in reducing the computational time.
But the fact that they deal also with lower order derivatives, right? Because they have it's in integral form. That because taking higher derivatives is expensive too.
Yes, but in original DEM also we have used the variational form, so that that also has lower order derivatives than the strong form.
Oh, DEM uses deep energy method. Yes, so they use the integral form, right?
Yes.
I see.
Yeah, actually, in my test, I also find that the integral, like getting this total energy, is quicker than using the strong form residual. So in later of all my cases, I switched to the energy formulation.
So in your paper, the long paper you have now, everything is in the energy?
No, strong form. That is strong form.
That's a strong form, yeah.
Yeah.
Okay. But because there you get too many iterations, I think, millions. Of course. Now here the geometry doesn't actually change, right? It's linear elasticity. You don't have like finite deformations, right?
No.
I see.
What I found interesting is that here, since they are changing from physical domain to parametric domain, and the parametric domain is always between 0 and 1, and it's a square. So the best application of this would be in transfer learning, because then they can change from one domain to another, and they can obtain the solutions in another domain. Like they can change the boundary conditions and they can obtain the solution. That could be a good application of this.
Can we replace the splines with a neural network? The geometry representation, and so when you take the derivative of the Jacobian, that will be like the neural network.
Could be.
It's just a basis, right?
Yes, it's a basis.
It's a good basis, but
Yeah, that could be done.
You think it could be done, Enrui or anybody else?
You mean the spline stuff?
Yeah. The geometry representation.
Yeah, I think so. I think that can be.
It's just a function.
Done. Yeah. Mm-hmm. And is there any other questions for Somdatta?
Hello, I'm sorry, I have a question if it is possible. Can you please go to the slide about changing from the original space to the mapped space? Yeah, so I think also it's asked before, but are you sure? Yeah.
Yeah, this one.
Yeah, are you sure if it is not connected to the space, it can still be changed to this parametric domain, which is a square shape? Because I don't know, maybe you can actually think about it as a topological algebraic topology. I'm not sure if it's, for example, ring, because there was a problem that you had it and there was a empty circle. So they were forced to, I think, to make it a 1/4 of the shape to be able to transfer it. Are you sure it's always possible to transfer it from physical domain to parametric domain?
Yes, I'm sure it can. Like we can always transfer four edge geometry to a parametric domain.
Okay, but if that space, the physical space is not full, how can you do that?
Um,
If the boundary conditions, for example, exist in the middle too, like the example you had, how you can do that?
You can always introduce some kind of discontinuity to show that. And you can incorporate, you can break your domain, like you can have multiple patches. Like you just don't need to do this in one patch. Like since it's a very simple geometry, they have defined it through one patch. They can connect multiple patches together and make their domain. If you want to introduce any kind of like circular or any form inside the in the domain.
Okay, that's if this is the answer. Thank you. Yeah.
Can I ask a quick question?
Yes, Exam.
So this is a song from Brown. First of all, how many networks they have here? So you said that they have one network for the displacement U1 and U2 and one network for the strain. So this is all the networks that they consider here?
In elasticity, they have considered only one network.
Okay.
In the strain gradient part, they have considered two networks. So in the first network, they take the displacements as output, and in the second network, they take the the strain gradients as output. And once they take in network one, when they get the displacement as outputs, they compute the strains, and then they take a difference between the strains computed through displacement and the strain which is obtained as output from the second network, and they also use that as a they use that in the loss function.
Okay, yeah, that makes sense. So my question is about the domain decomposition that they have. So if they have, like, let's go to the case of the elasticity that you said that they have one network. So when they have the domain decomposition, then it's basically the integral that they are computing over different elements, right? So the approximation is just one. So you have one single global network. Is that correct?
Yes.
Okay, I see. So it's just the composition of the integral, correct?
Yes.
Okay, I see. All right, thanks. I just wanted to make sure that I understand this correctly.
Welcome.
Okay. Thank you again, Somdatta, for your presentation.
Thank you.
And
I'll stop sharing.
yes, please. So now let's welcome our second speaker, Liu, also from our group, and he will present a paper review with title Deep Physical Neural Networks Enabled by a Backpropagation Algorithm for Arbitrary Physical Systems. So Liu, can you share the screen?
Yeah.
Yeah.
Can you see the screen?
Yeah, we can see that.
Yeah. So yeah, this is I'll present this paper. Researchers from the Cornell University. Actually, before jumping into the details, I want to actually take a close look at this paper. So it's deep physical neural networks. It's not deep physically informed neural networks. Actually, he's literally proposed some neural network that is literally built with the physical system. So you literally have like an optic system or a mechanical system or an electronic system as a neural network that can also do something like neural networks. Okay. The motivation is the emerging deep neural networks energy problem has inspired the special proposed hardware deep neural network accelerators. Several proposals push beyond the conventional electronics with alternative physical platforms such as optics. Yeah, so traditional. Well, we have seen is basically we play with the silicon chip and the matrix multiplication and the addition and nonlinearity are basically calculated in the chip, but that is a little bit time energy consuming, and now researchers are looking into, for example, using other physical systems to do this kind of stuff. More generally, the controlled evolutions of the physical systems are well suited to realize deep learning models. So that in general can be more than optics, literally like other systems. DNA and physical processes share numerous structural similarity, such as hierarchy. That is to say, the deep neural network is like a composition of functions, and the same thing can be happen in the physical process. Approximate symmetries, well, for example, is rotation symmetry, permutation symmetry, something like that. Redundancy or over parameterization, and nonlinearity. Okay, so the point is that we can harness these physical computations by encoding input data into the initial condition of the physical system and read out the results by performing measurements after the system evolved. So this can be viewed as an analogy of a neural network layer. And the physical computation can be controlled by adjusting the physical parameters. That is, that can be make an analogy of the parameters in the neural network. By cascading such controlled physical input-output transformers, we can realize trainable hierarchical physical computations. That is a deep physical neural networks. So here in A is a traditional neural network. What do we see every day? And this is like a physical neural networks. You can see, for example, a mechanic system, an optic system, or electronic system can act as an operator, nonlinear operator that maps the parameters and input into the output like this. And well, we can build because this is actually one module or one layer, and we can have a lot of layers like this, and then we can have a hierarchical physical computation. And I want to talk about the related works. So there have been few experimental studies on physical learning hardware. However, and those that exist have relied on gradient-free learning algorithms. And well, gradient-free learning basically, the author claimed that gradient-based learning algorithms are essential for the efficient training and good generalization of large-scale deep neural networks. I'm not sure what does mean by larger, what kind of scale neural networks, but it seems to me that some method based on genetic algorithm can also tackle neural networks. To solve this problem, proposal to realize backpropagation on physical hardware have appeared. While inspirational, these proposals nonetheless often rely on restrictive assumptions such as linearity or dissipation-free evolution. So basically, say that the other researchers have done something with restricted physical systems, but well, the most general proposal may overcome such constraint, but still rely on performing training in silico. In silico, that means using computer to train. That is to say, is wholly within the numerical simulation. Therefore, to be realized experimentally and in scalable hardware, they often face the same challenge as a hardware based on mathematical analogies. You need intense engineering efforts to force the hardware to precisely match the idealized simulation. I will come back to this topic later. So the author point is, okay, if you fully build like a digital model of the real physical system, or like a digital twins, and you train in your computer, then that part gonna be pretty. You need a lot of effort to make your model very precise, and that's gonna be sometimes impossible. So this is what the author proposed. They proposed like a hybrid physical digital algorithm, what they call physics aware training, or PAT. The basic idea is actually, say, in the as we know, to do backpropagation or calculate the gradient, we actually need a forward propagation first. So the forward propagation is actually performed in the physical system, literally in a physical system, nothing to do with the model, nothing to do with simulation. For example, if you send the input and parameters into this physical system, and the output is like this, and then you calculate the vector error, you calculate the error, and then for the backpropagation, you will actually still need a model to do the differentiation, because the physical model is not differentiable. It's just like a model there. You don't know the differentiation. So you basically need a model to calculate differentiation, and then you get the gradient. I will go to the details of this part in the next slide. But here the author shows the comparison between the hybrid algorithm and the pure on silica approach. So this blue one and is the physical digital hybrid physical digital algorithm they proposed, and the black one is just purely trained in the simulation or in the model. You can see that in the end, this one is it's not really better than random guessing, but this one is it's like pretty much better. And here he shows that he actually shows us so as we increase the number of layers, so this one will, you can see the improvement of the performance, but for this one you can see nothing. So that is the conclusion. Okay, so in this slide I'm going to introduce the detail of the hybrid algorithm. So this is the forward pass. FP is P represent the stands for physical. So you can see FP is like a operator that takes the input x and parameter theta as the input and output something or y1. And y1 is also like say is also act as the input of the next layer, and it's the x2. You get and theta2 is the parameter in the second layer, like this. So this part is physical. It is realized in the physical system, and then you get prediction, and you get and you have target, and you compute the error. Of course, this error is I believe this error is calculated by the computer, and then you get, okay. Maybe we should take a look at this. So y is fp x theta. So this is like one layer stuff, and then the gradient of gx is partial L partial x equal to partial, well, ideally it should be partial f partial p partial x xt transpose g. Gy is a partial L partial y. Ideally you should do like a p here, but you don't know the physical, the gradient of the physical model. So you have an alternative, a surrogate to calculate this. But still, notice that here you need to put the x here or x here, x here, x here. The point is that you don't calculate the x3, x2, x1 from the simulation. You calculate x from using the physical system. So that is why it is hybrided. You say, okay, this part is digital, is simulation, is surrogate, but this part is calculated in the physical system. Any questions?
Hi, this is Apostolos. So what does it mean that the G's are estimators of the gradients?
Oh, it's a, well, if this is, okay, sorry, if this is like just like a one layer stuff, then it's just the gradient.
Okay.
Yeah. Well, actually, you see that like gx is well, okay. Okay, sorry. I should put it in this way. If this is like a one layer stuff, then partial L partial y can be calculated analytically. Nothing, right? And but the partial L partial x, so this one, ideally you should do partial fp, the physical model partial x, but you don't know that, so you replace f with a model. So that is actually approximation. So partial L partial x is always approximation. So is partial L partial theta.
I still can't see it, but okay. I thought like dl over dy we can have them exactly, but
oh well, this part is if this is one layer stuff, then this is
okay.
This is analytical like this. If y is fp x theta, then this one can be calculated analytically, but this one you cannot because you don't know partial fp partial x, right?
Yeah, that one, yes. Okay. Yeah. You're right.
you replace the FP here with FM. That is why it is estimator. Yeah.
Okay, thanks. I was talking mainly about GY actually.
Oh,
yeah, but...
I mean, if okay, I mean, if it's one layer, then I think it's analytical. But if it's multi-layer, this is why. Even for this Y, for example, this Y, you still have,
you still have the rest. Okay, I see.
Yeah, that is, I think that is their point.
Yeah, thanks a lot.
Okay. Now we go to the physical system. Actually, they tried the three systems: the optics, the mechanics, and the electronics. Electrics. Anyway, electrics. So I start with the optical one. So the input and the output are some parameters. Actually, they are both 50 dimensional, except the first layer, but that's not important. So basically, we have a 100 dimensional vector, and then this is a spectral. So this is a spectral of something. So basically, they encode this 100 dimensional vector into this spectral, and they use a pulse shaper, which I don't know what is that, to map a laser to something else with a different. So now you can see that this vector is encoded in this stuff, and then you have another operator, which I don't know either, and then you get another spectrum, and then the output is something like this. So here there's no, so in this part there's no calculation, calculation in the computer at all. It's all the nonlinearity, or maybe there's like convolution, because I don't know. I'll basically realize by this physics. Okay, and this is like one layer, so the input parameters to the output. But you can see that the scale is different. Then basically, so this is the whole stuff. I'll go to it. The orange ones are some trainable rescaling. So basically, you need to rescale this, rescale the for example, the output. Otherwise, you cannot concatenate with parameters to the next input because it's scale different. And the orange, the green one are the untrainable residing summation. Basically, it's just a reshape, and nothing important. And the purple ones are the physical input-output transformation. Okay, so the input is a 12-dimensional vector of vowel formatting frequencies. Anyway, it's just 12-dimensional stuff input, 1D rescaling, trainable, and repeating. So it's just repeating 4 times. And this is together with a 52-dimensional vector of trainable parameters as input. And then the total input is 100-dimensional. And you go through this physical transformation, you get a 50-dimensional output. And then you have another rescaling. So here 1D rescaling just means the elementary element-wise rescaling. So you can see that basically here is 50 trainable variables, or maybe 100. I forgot if they have a bias or not. Maybe they don't have bias. And then you repeat this for 5 times, and in the end you have 5D-dimensional stuff, 50-dimensional vector renormalized with the 10. Renormalized with 1D as before, and then okay, you do some crop, you do some summation, and do the argmax to do the. So this is going to be the prediction, output prediction. This is classification problem, and here are the results. So it is like we have 7 categories, and so this is a true label. This is the predicted label. So basically, the test accuracy is 93%. Yeah, that's it. And here I show 2 examples. So this is the spectral. Well, for this one, okay, you basically have like a beans, 7 beans, and you can see, okay, this bean is has the most well, is largest. And then, so we can see, okay, the prediction is and similar for this one. So that is what they do. Yeah, the direct output is spectral, but then you need to do some yeah, to do some classification based on this spectral. Okay, and then it's a mechanic system. Actually, I think the mechanic system is actually a little bit boring because they also remark that this one is not nonlinear. It's actually a linear operator. But nevertheless, I will. So the point is, so this is like the input is a mnist digit. It's a 384 dimensional vector, and then you basically still do like rescaling. It's elementary wise rescaling with some trainable parameters, and then go to this operator. Again, this is a linear operator, so it's actually a little bit boring. And repeat it for 3 times, and in the end you crop at the summation, and another 1D. I think here is like a bit weird. I think it should be 10D. It's like but anyway, it's a trainable rescaling, and then you do the argmax. That's it. Here they are showing the compare. Okay, so the blue one is the is the result for this system. But okay, they claim that the author claims that if you remove these three physical systems, or just replace these 3 physical systems with the identical operator, then you basically get this black one to show that although this is kind of simple, but these 3 operators are still important. Yeah, maybe they are right, because even if it's linear, this can still, okay, let me put it this way. So here, all the operations are element wise. So you cannot really mix the information between different channels or between different pixels. But here, this 3 physical transformation will do some mixture or hybrid to make I should say to merge the information in different pixels. Make sense? Yes. So that's a difference. And then this is the electronics system. Okay, this is something I have no idea what it is at all. But this interesting here is actually they say, okay, well, let me put it this way. So this part is just similar to the mechanical ones, but the difference is that they actually have 7 channels. Well, 7 total copies. The copy just means the structure is the same, but the trainable variables are different. They are independent trend. And then in the end, they will average the outputs of the 7 channels, and then take the argmax. So basically, you can see that this is depth and this is width. And also you can see the difference. So that the point is these three physical transformation are critical. Okay. So actually, I will show the main results, but I still didn't really talk about how they build the model. This is what they do. They actually use a deep neural network to build a data-driven digital model, or like a surrogate. So they use a neural architecture search, find the optimal deep neural network architectures allowed for the most accurate digital model across the physical system we considered. And so this was their default approach. So they first collect training data by recording the output of the physical system for selection of n input parameter vectors, where n is usually like 10 to the 4. This is this scale, and the input parameter vector are usually sampled from a uniform distribution. So this data set consists of the data will split into training and validation setup, training and validation, just like standard setup. And here are how they perform neural architecture search. This neural number is between 1 and 5, and each layer is between this one. and the initial learning is like this one. So for the SHG, so this is the optic one, the optic system, the optimal architecture was found to be deep neural networks like this, and this is the electronic circuits like this. And for the oscillating plate, that is the mechanical one. They initially tried to find a deep neural network architecture, but then realized that this system is linear. So like a neural network with no hidden layer, that's basically a linear operator. So that's it. And here I show the results of so show how accurate the model can be. So again, so this is like the 100 dimensional to 50 dimensional optic one. And here I think here I show 3 examples of the input to output map. This is the first one. You can see the orange are the trainable parameters. The red one is the input data. You can see like this. And here are the prediction of a data-driven model against the ground truth that is produced by the experiments. Actually, this is very, very well. I think this is like this is actually the foundation, the ground, why they can make it. Actually, I'm a little bit surprised to see that, because this is like literally 100 dimension. It's not like say the it is represented in one, but it is like say the essentially the intrinsic dimension is 100 dimension. Yet they use like 10 to the 4 prime data to learn this function, very, very complex function. I feel I'm a little bit like surprised about this, because well, usually, for example, usually like an image, it can be like several hundred dimensional, but the intrinsic dimension is not that much. We can maybe use like even 10 dimension to express this, like maybe light in the 10 dimensional manifold. But however, I mean, since the input parameter vector are usually drawn from uniform distribution, this is literally 100 dimension. Okay, I did okay, but they also show the other the similar thing for the other 2 systems, but that is a little bit that is not that interesting compared with this one, so I will just omit it. In the end, I want to have a discussion like why a hybrid physical digital algorithm helps. So with the PAT, physically aware training, even if the gradient are estimated only approximately, the true loss function is always precisely known. This one is always precisely known. Moreover, the true output from each intermediate layer is also known. This is all the X here is always known. So the gradient of the intermediate physical layer are always computed with respect to the input, correct input. That is to say, at least your input is always correct, although this partial FM is approximation of FP. In contrast, in any form of cyclical training just means to replace FP here with a model. That is, everything is performed in the model. Compounding error built up through the simulation of each physical layer, lead to a rapid diverging simulation reality gap as the training proceeds. That is to say, okay, for example, here you will replace FP with FM. Then for the output, you have, for example, 0.1 error. And then for here, for the X3 gonna maybe have like 10% error. Sorry, this is 1%, this is 10%, and later it's gonna be like maybe 100%. And then basically you estimate the gradient in the wrong place. Then you fail. So I think this is like the key idea why this hybrid algorithm is better than pure in silico training. Okay, that's all. I think that's basically this paper. Yeah, thank you. Any questions?
Hi, Liu.
Yeah.
I don't quite understand why the true loss function is always precisely though. No, I do not quite
Oh, so
get that.
okay, the true loss function is basically use the prediction, prediction and the ground truth, right? But this prediction is the forward part is performed in the real system, in the real physical system. That is why they say it's precisely known. It's not the prediction doesn't come from the simulation. It comes from the real system.
Okay, I see. So they call this the so-called true loss function.
Oh well, yeah. I think here so this is like say if you are using the pure physical system, then this is what you want. Okay, let me put it this way. In the end, what do you want? In the end, you want to use this true physical system as a predictor. This is in the end what you want. And this prediction is of course it just comes from the thing you want. So we call it the true one. But if you use something like a surrogate, then you call it like it's not true, right?
Okay, I see. Yeah, thank you.
Yeah, thank you.
And is there any other questions for Liu? Yeah, if not, let's thank Liu again for giving this presentation. And so this ends our current seminar for this week, and hope everyone have a safe and nice weekend, and see you the next week. Bye-bye.
Thank you, Andrew. Thanks for hosting.
Thank you.
Thank you.